Now that we saw conceptually how the backpropagation algorithm works, I wanted to go over a practical example of actually doing it with PyTorch and cover some of the gotchas of PyTorch's automatic differentiation module. Here I am in another Jupyter notebook, and I've already imported Torch and created a example tensor for us to work with here. And I want to draw your attention to this argument requires grad equals true. Since this is really what tells PyTorch that we actually are eventually going to need gradients and we're doing backpropagation for this tensor x. And you can think of this requires grad equals true as signaling to PyTorch that x in this case is one of those leaf nodes or input variables that we're going to need to compute gradients for. And we're going to be backpropagating over a very similar function to the function from last video, the conceptual introduction to backpropagation. The only difference being that instead of being a function of two variables x and y, for the sake of ease of visualization, we're making this a function of just x, but the form is the same, 3x squared plus 2x rather than plus 2y here. And one thing to note when working with tensors and kind of functions in PyTorch is that the shapes end up propagating through. So since x in this case is a 10 length tensor and x here is a 10 length tensor, we're adding two 10 length tensors together. Y in this case has 10 elements. And I'll talk about why that's important a little bit later in the video, but notice that in addition to x having this additional, call it attribute, y also does. Y has a grad function attribute, even though we never really signaled to PyTorch when creating y that it has anything to do with gradients or requires grad. This just gets basically propagated from x, and since y is a function of x, this gradient kind of flag ends up getting propagated through. If you remember back to our computational graph, the node that represents y in this case needs to know both how to compute its outputs or its forward pass as well as its gradient or its backwards pass for kind of the local gradient of just that node. And to intentionally show an error here, if we try to plot this, and if we try to just convert these x's and y's to NumPy arrays to then plot, we see we have an error here that says we need to use detach NumPy instead. And the reason we need to do this is, remember, we have requires grad equals true, and detach essentially creates a copy of the computational graph, or it removes whatever we call it on from the current computational graph that has requires grad true, and instead makes it not require any gradients, which signals to PyTorch that we're really only using the values of what we're getting back from this tensor. And to kind of show that this is the case, we can call x.detach and then call requires grad on the output of that and see that we have false here. And this would be kind of equivalent to just initializing a new tensor x with the argument requires grad set to false. So .detach is just a quick way and kind of a convenience function to take the same values of what's in x and remove it from the current computational graph, which is kind of this means of signaling we're just using these values, we're not doing anything with gradients about it. And the magic of automatic differentiation in PyTorch is that to compute the backpropagation algorithm or pass, it's really only this one function call, y.backwards, and you call it on basically the output that you want to start your backpropagation from. In this case, since y is kind of the result of our function, we call backwards on the output, and this essentially propagates throughout the function. It looks at what tensors the function depends on, and then it looks at which one of those tensors requires gradients, or is it part of a computation that has a tensor that requires a gradient. So it kind of, as the name implies, backpropagates through until it gets to a leaf node. And remember, a leaf node in this case is just a kind of base case tensor that requires grad equals true. And another thing to note about this is that nothing actually changed. It didn't output anything within this cell. And it's important to know that the way that this backpropagation works is that the gradients essentially accumulate on the leaf nodes and they happen in place. I'll kind of go through an example, reinitialize this. If we call x.grad before calling backwards, we essentially get returned none because the gradients haven't been computed yet. Once we call y.backwards, we now have gradients on x. And notice that there's actually 10 elements here. And that's because what x.grad really is something similar to dy dx1, dy dx2, dy dx, call it m. So this x.gradient is going to have as many elements as x has, and these are going to be the derivatives of the output, or whatever we called our backwards on, with respect to each one of these components. And the last bit to note here with this backpropagation, you don't often see or need to include this gradient argument to the parameter. In this case, we set it to just an array or a tensor of all ones. And this is usually the case of when you do need to include it, you always kind of just set it to all ones. And the reason you need this is that y is actually a vector or a tensor itself with 10 elements. We need to pass into the backwards function basically what gradients we want to start with in the backpropagation. And to kind of pull that apart a little bit more, we can actually go back here, create a copy of x, create a copy of y, and then create a third output or a third variable that's going to be basically the sum of all of our y. And the reason I wanted to do this to show you is that if you have a tensor or a non-scalar output that you're calling your backpropagation on, in this case when y has 10 elements, we need to pass in 10 ones essentially. But when we have z as a scalar, it's just a single number. PyTorch internally basically starts backwards propagation with a single one. So if we call z.backwards, notice here that z.backwards doesn't have any gradients argument. And usually when you're training neural networks, when you have scalar valued loss functions, this is most often what and kind of how the function call looks. And to just show you the gradients again here, so the gradients are identical, even though z in this case is the sum of all of our y's. You might think that the actual gradients are changing for x, but again, remember what these gradients are. These are the single kind of output. In this case, it's going to be z, so it's dz dx1. And this really corresponds to how much does z change when we change the first element of x. And this should be identical to how much y changes when we change the first element of x, because z is just the sum of y. So anytime x1 is going to change y, it's going to equally change z by that much. And again, x here has 10 elements, or x.grad has 10 elements, because this is dz dx1, dz dx2, dz dx, all the way to however many elements x has. So to plot our original function y, not z in this case, we can use detach on both of x and y to basically, again, remove it from the computational graph that requires grad. And if we want to visualize the gradient, we can either use detach both on x and x before we call grad on it, or we can use kind of the shorthand in torch, or this kind of context operator, torch.autograd, and this has the same effect. It basically says everything in this block, we're detaching it from the current computational graph. This is basically just equivalent to calling .detach on every tensor that requires grad. And if we plot this, we can see we have a straight constant line. And if we go back to our function, we thankfully by hand can compute the symbolic gradient of this, which is just going to be 6x plus 2. And if we scroll down, indeed, this line is the line 6x plus 2. It's just a linear function of x, and that's because there's the x squared in there. And the last bit I just want to go over is to kind of show an example of this idea of gradients accumulating, which I kind of mentioned quickly and breezed right over it. But when you are using backpropagation, the dot backwards function in practice, you're usually in the context of training a neural network. You're running some for loop over some amount of iterations, mini batches, epochs, and you're computing backwards over and over again. So here, kind of the maybe naive approach would be, all right, we have x.grad, we're just printing it out to kind of see how it progresses. We have our y function, y is a function of x, and we're calling backwards. And each time in this loop, we're calling y backwards. And maybe instead of just printing x.grad, we're actually doing something. We're updating the parameters of our neural network. Now, notice here that every call to print x.grad, every new time through the loop, the gradients essentially just get added to whatever was there. We start off with 2, 2.6, 3.2. We go to 4, 5.2, 6.4. We add another 2, 2.6, 3.2, and so forth. So every time we're calling that backwards, since it updates things in place, again, this doesn't return the gradients. This just propagates through the existing graph and updates at the leaf nodes, in this case x, what those gradients are. And the way it does this update is it basically sums or just adds them together. And the kind of fix for this, or the convention when you are training a actual neural network, is to zero out the gradients before every iteration. So here, if we call x.grad.0, it has the effect of basically zeroing out the gradients for whatever we're calling it on. And here, notice that the gradient, this is what's left over from our last iteration when we didn't zero things out. It starts, instead of as none, it basically starts as whatever the last kind of computed gradient was, which is this sum of all the gradients. But now when we have zeroing out gradients in our for loop, we essentially get the same value for every iteration after we're calling .0. And now if we run this loop again, every time we run the loop, it's always going to return the same gradient. Since we're zeroing things out correctly, we're defining our function and we're calling our backwards pass. And this is actually important to define our function or kind of redefine the output inside this loop. If we don't, it essentially throws an error that we're trying to backpropagate through a graph a second time, since y doesn't get reinitialized. But whenever we reinitialize y without reinitializing x, we essentially are creating a new graph, since any new variable we create, y as a function of x, basically signals to PyTorch, create a new computational graph, and use this for the backpropagation that we're calling on y here. And that's about the end of our lightning tour of backpropagation in PyTorch and the AutoGrad module, covering kind of some of the gotchas. In practice, when you are training a neural network, when you are using PyTorch's built-in optimizers, you don't necessarily need to get down at this level of granularity, but I just wanted to show you, kind of pull back the covers of how powerful just the kind of plain AutoGrad module is without all of the neural network machinery built around it. But in the next video, we're going to look at how to actually train a real neural network end to end. And that's going to be kind of the end cap to this Intro to PyTorch series.